Greeting, guys and girls. Today I want to kick off the last thing we're going to talk about this year, which is acids and bases. Always a quick pit stop at the end of the year. We're not going to go into crazy depth about these, but we're going to get at least the basics of acids and bases under your belt. And today that's going to be an introduction into acids. And then I've attached a video to remind you how we name acids or write the formulas of acids, which we did earlier this year. So that should all be reviewed. So if we're going to talk properties of acids, we would want to be able to identify one. How do they know by its characteristics what an acid is before we get to the molecular level? So all acids have the same 5 characteristics in common. First one is that they taste sour. Once upon a time, believe it or not, that used to be a very common way of testing chemical properties, was by taste. And they found out that acids have a sour taste, sometimes a tart taste. So a lot of fruits have acids in them. Right? So lemons have acids in them. That's the sour they're referring to. But the tart is more like what you would taste from an apple. Maybe a crab apple or something like that. If we're in the lab and we put what we call an indicator into it, acids change the color of indicator to red. On a pH paper, the more red, the more acidic. There'll be like various shades of red. On a simple litmus paper, red litmus paper stays red, blue litmus paper turns blue. Third characteristic is that acids react with metals to produce hydrogen gas. And the reason for this has to do with what we do to predict reactions. If I take any acid, you're going to find out that a characteristic of an acid is that they all begin with hydrogen. So if I pick an acid like hydrogen chloride, which we would call hydrochloric acid, and I put it with a metal, anything that lives to the left of the periodic table, like magnesium, as long as the metal is active enough, what will happen is we find like charges and trade for this single replacement. So we've got the hydrogen as a positive, the chloride is a negative, and magnesium is a positive. The hydrogen and the magnesium will trade. So the reason why acids always create hydrogen gas when put with a metal is all metals carry a positive charge. And in all acid, the hydrogen is the positively charged species. So we would get magnesium chloride plus the hydrogen ends up by itself. Right? So that has to just do with regular old-fashioned properties of single replacement reactions. Right? Other things that we want to know about acids is acids react with bases to produce salt and water. And remember, not all salts are table salt, like the type you put on your French fries, sodium chloride. A salt is any ionic compound. And so whenever you find that you put an acid with a base, you're always going to get water as one product, and you're going to get some sort of metal with a non-metal, right, which is by definition a salt. And some acids conduct electric currents. Right? You're going to find out strong acids conduct them very well. They're strong electrolytes. And that weak acids don't conduct it as well. All right? There's less ions. It is a weak electrolyte. So if we get more into the molecular level, you're going to find out that there's 3 different types of acids, and each one is a little different than the other because they expanded the definition as they found more and more things that fit the characteristics of acids. But the first is the most specific definition. It's called the Irenaeus Model. And in the Irenaeus Model, it's a very straightforward definition. It says that acids are any substances that produce H plus or H3O plus when they're put with water. So if we put the hydrogen chloride with water, the H moves over to here, and we get H3O plus and Cl negative. We get HBr reacting with water to get H3O plus and Br negative. We get HClO2. With water, we create H3O plus and ClO2 negative. So any substance that creates this ion, which is known as the hydronium ion, it is by definition an Irenaeus model. And that's the most specific because you have to make this exact ion. Well, what they found out is there were substances that didn't necessarily create the H3O plus, but still had all the other characteristics of acids. All right, so another set of scientists came along, Bronsted, Lowry, all right, and they, or he, I can't remember if that's a surname or two different people, they said an acid is simply a proton donor. It's an H plus giver. So if we put HCl with water, the HCl turns into Cl negative. So it gives its H to water, right, by the process that you see down here. Right? The H goes with the water and it leaves behind the electrons. So think of it as like the Cl is allowing the H to leave. Now, if the acid is giving the H to water, it is also going to be an Irenaeus because it creates H3O plus. Because when the water accepts the H, you get H3O plus. So sometimes a Bronsted-Lowry is also an Irenaeus, but sometimes it is not. Right? If we wanted to look at one that wasn't, right, we would look at this one. We take NH3, and NH3 turns into NH2 negative, so it's missing a proton, so it's a proton donor. Right? It gives it to the water, so it makes H3O plus. So because there's the hydronium, it is also a Irenaeus acid, as was this one, the HBr. Right? To show you one that isn't, I would do something like this. Let's say we took HCl and I put it with ammonia, NH3. What can happen is the HCl will give its H to the ammonia, creating NH4 plus and leaving behind the Cl negative. And it's donated a proton. It has given a proton away, but notice what you don't see over here. There is no H3O plus ion. We have NH4 plus and we have Cl negative. So this is a Bronsted-Lowry acid, but it is not an Irenaeus. So that's what one would look like if it were a Bronsted acid, but it were not an Irenaeus acid. All right, so the long and short of it is you look at the two things that seem to be similar on each side, the ones that look alike, and figure out what's happening with the proton. Here, the H is leaving the Cl and going to the NH3, so there's my proton donor, must be my acid. All right, the last type is the least specific. A lot of things meet this criteria. A third scientist said, well, there's still a category of things that sort of act like acids, but they don't necessarily have to possess hydrogen. Right? To be an acid for Bronsted, you're a proton donor. But what happens whenever you give that proton away, you keep the electron. So you're an electron pair acceptor. All right, so what Lewis said is, well, let's get more generic. Any substance that just accepts electrons should be an acid, doesn't even have to have hydrogen. And the Lewis acid is probably the least useful of the three. Bronsted is the most useful and most common of the three. So we'll want to know this in definition, but in terms of being able to identify it, I mostly need you to be able to see Bronsted and Irenaeus acids. Right, so tomorrow we're going to get into acid dissociation and how they break down and strength of acids. But the rest of the time for today is going to be to jump on to the other video where I'm reminding you how we write the names of acids and we write the formulas of acids. I hope everybody is doing well. Feel free to shoot me a Parent Square message or an email if you're having any questions. No formal meeting. All right, today later at 1 o'clock, it is Scarlett's birthday, in fact. All right, so we're going to have birthday events going on within the family. I hope everybody's doing good and staying healthy. Miss all you guys, and I hope to see you soon.